Welcome back. In this video, we'll explore the force acting on a surface submerged in a liquid of known density and derive a general expression that applies across different scenarios. Before we dive in, I recommend checking out my previous videos where I break down the fundamental concepts. If you're already comfortable with those basics, feel free to continue with this one. Let's consider a wooden gate submerged in water, inclined at an angle theta from the horizontal. The vertical distance from the surface of the water to the top of the gate is h1 and to the bottom is h2. Based on what we've already discussed, pressure in a liquid increases steadily with depth. That means the deeper you go, the higher the pressure. Force is defined as the pressure applied over a unit area, and since it is a vector, it has both magnitude and direction. In the case of a submerged gate, this force acts perpendicular to the surface of the gate. The deeper you go, the greater the pressure, so the force increases from top to bottom. What you see on the screen is how the force is distributed along the gate. Our first step is to figure out how much total force the fluid applies to the gate. After that, we'll find out where exactly this force acts. This point is called the center of pressure. Before we begin the analysis, let's establish our coordinate system. We'll align the y-axis along the surface of the gate, starting from the top edge as the origin and increasing downward. The x-axis will point directly outward from the gate, perpendicular to the screen, towards the observer. Now, if we view the gate directly from the front, its surface becomes clearly visible, and we can also see how the coordinate axes are positioned across it. On this side of the gate, we'll mark the distances to the top and bottom of the gate along the y-axis. Doing this helps simplify the calculations. Let's call the distance from the liquid's surface to the top of the gate y1 and the distance to the bottom of the gate y2. Alright, picture this. We take a very thin horizontal strip across the gate. Let's say it has an area delta A. This strip lies at a depth h below the surface, and it runs along the x-axis. Now, just to be clear, y is the distance from the liquid surface down to the strip, measured along the y-axis. Since the height of the strip delta A is extremely small, and it lies flat at a constant depth, the pressure across the entire strip doesn't change. That means we can safely assume the pressure is uniform along that strip. So the force on this tiny strip is simply the pressure at that depth multiplied by its area. This pressure is calculated by multiplying the density of the liquid ρ, the gravitational acceleration g, and the depth h below the surface. We can express the vertical depth h in terms of the coordinate y along the slanted gate as y sine theta. Now, to find the resultant force acting on the gate, we integrate the pressure over the entire submerged surface area. Since pressure varies with depth, and hence with position along the gate, we add up the small force contributions from each strip. After pulling out the constants from the integral, we arrive at an expression that gives us the total or resultant force acting on the gate. Now, what does this integral represent in the expression? It's actually the first moment of area about the x-axis. In simpler terms, it's the product of the total area of the surface and the vertical distance from the x-axis to the centroid of that surface. Suppose the gate is a simple rectangle instead of a complex shape, then the centroid is located midway along the length and width of the object. So, if the gate is submerged vertically, the centroid would be halfway between the top and bottom edges, and the depth to this point is what we use when calculating the total hydrostatic force. What's important to note is that the centroid is not where the resultant force actually acts. We use the depth to the centroid only to calculate the magnitude of the resultant force. Now we can replace the integral in the expression with the product of the gate's area and the depth to its centroid. To simplify things further, we substitute the vertical depth to the centroid, that is, hc, in place of yc sine theta. This result gives us the total hydrostatic force acting on a flat surface submerged in a liquid at any angle. What makes it so useful is that it works for all kinds of flat surfaces, whether they're vertical, horizontal, or inclined. Okay, now that we know the total force acting on the surface, let's move on to the next step, finding where exactly this force acts. In other words, we're going to find the center of pressure. To do this, we apply the principle of moment balance. The idea is that the moment produced by the distributed pressure force across the surface must be the same as the moment produced by the single resultant force acting at the center of pressure. It's important to note that we arrived at this expression because we took moments about the x-axis, but this isn't the only option. The moment can be taken about any point. In the previous section, we derived an expression for delta F. Now, by substituting that into the equation, we get the result you see on the screen. Since rho g and sine theta are constants, we can take them outside the integral. What remains is the second moment of area, about the x-axis. This is also known as the area moment of inertia, a measure of how a surface's area is distributed relative to a given axis. In our case, it's about the x-axis. It tells us how resistant a shape is to bending, or how pressure is distributed when calculating the center of pressure in hydrostatics. So, instead of evaluating the full integral, we can replace it with the second moment of area about the x-axis, which is written as I sub xx. This substitution simplifies the expression and helps us move forward in calculating the center of pressure more efficiently. The term I sub xx, or the second moment of area about the x-axis, tells us how the surface area is spread out relative to that axis. But here's the catch. Most standard values you find in tables are calculated about the centroid of the shape, not about some other axis, like the x-axis we're using in this example. So what do? That's where the parallel axis theorem comes in. It helps us adjust the centroidal value to fit our needs. The rule is simple. You take the moment of inertia about the centroid, which we usually have from a table, and add the area of the surface multiplied by the square of the distance between the centroid and the x-axis. Now, applying the parallel axis theorem, we substitute the moment of inertia about the x-axis and update the moment balance equation accordingly. Earlier, we derived an expression for the resultant force acting on the surface. By substituting that into our current equation and canceling out the common terms on both sides, we arrive at a much simpler formula. This gives us the location of the center of pressure along the y-axis. To find the vertical distance h sub r from the liquid surface to this point, we can use a simple trigonometric relationship based on the angle of the gate. This final expression gives us the exact depth to the center of pressure, the point where the resultant hydrostatic force effectively acts on the surface. It's a key result in fluid statics, especially useful when analyzing submerged surfaces under varying pressure distributions. Before we continue with the video, I kindly ask that you to give a thumbs up, subscribe to my channel, and click the notification bell. Your support is much appreciated. Thank you. Let's get back to the video. Okay, now, we need to determine the distance to the center of pressure from the y-axis. Just as we did earlier, this involves taking moments, but this time, we'll take the moment about the y-axis to find the horizontal location where the resultant force acts. Let's now bring in the earlier expressions we used for the small force delta F and the total resultant force and substitute them into the equation for moments. When we do that, the equation now includes an integral that represents how the area is spread out with respect to both the x and y axes. This integral is called the product moment of area, or more commonly, the product of inertia. It measures how the area is distributed relative to both the x and y axes, and it's especially useful when analyzing forces and moments acting on inclined or asymmetrical surfaces. In another video, I'll be covering the moment of inertia for different shapes and geometries, so stay tuned. Please don't forget to hit the bell icon so you'll be notified as soon as that video is released. All right, let's move on with the exercise and find the distance from the y-axis to the center of pressure. To do this, we'll replace the integral in the moment balance expression with the product of inertia. But it's important to understand that this is the product of inertia relative to the chosen axes, not the centroidal ones. To shift the reference from the general axes to the centroidal axes, we'll apply the parallel axes theorem. We'll use this to express the product of inertia about the centroid and continue solving for the location of the resultant force relative to the y-axis. This final expression gives us the distance from the center of pressure to the y-axis. But here's something important to note. If the surface is symmetric about the y-axis, the product of inertia becomes zero. In that case, the center of pressure lies directly on the y-axis. In this video, we explored how to calculate the resultant hydrostatic force on a submerged plane surface and determine its point of application, known as the center of pressure. The key takeaway is this: the magnitude of the resultant force on any plane surface submerged in a fluid is independent on the angle at which the surface is inclined. It depends only on the depth of the centroid from the surface of the liquid. The center of pressure, however, does depend on the inclination angle unless the surface is symmetrical about the y-axis, in which case it lies right on the axis. We also introduced key concepts like the first and second moments of area and how to use the parallel axis theorem to simplify our calculations. With that, I'll wrap up this video. I hope everything we covered was clear and easy to follow. In the next video, I'll walk you through more examples to help strengthen your understanding and boost your confidence with these concepts. So stay tuned by hitting subscribe and tapping the bell icon. Your support and feedback truly mean a lot to me. If you found this video helpful, please don't forget to give it a thumbs up. It really helps me know I'm on the right track. Until we meet again in another video, take care and goodbye.